multiple linear regression. Now, difference between simple linear regression and multiple linear regression is in multiple linear regression, see, there are different input columns, input variables. See, x1, x2, xn, etc. are the predicted variables or input variables. B0, B1, B2 are the coefficients. Okay, so it is similar to simple linear regression. So this is the equation for simple linear regression. Y is equal to B0 plus B1x. Okay, now when it comes to multiple linear regression, the equation becomes B0 plus B1 x1. So instead of x, here the first input x1 plus next coefficient, then second input x2 plus next etc. up to last. Okay, so I have shown some examples also. So, like the selling price of a house depends on different inputs. So, this is an example of multiple linear regression. The selling price, this is the output. Selling price, this is the output in this case, in this application. So, this Y depends on so many inputs. So, this is X1, this is x2, the number of bedrooms x2, the number of bathrooms x3. So that means if the output depends on many number of inputs and you require a prediction, so in that case you can use the multiple linear regression. For prediction purpose we will be using linear regression. Now since here multiple inputs are there, we are using multiple linear regression. But in the previous case, in the salary prediction case, we had only one input. So that's why that means only X and the output is only Y. For this Y, this X is the input variable. Only one input we had. So that's why we are used simple linear regression. But here, since there are multiple inputs, we have to go for multiple linear regression. And this is the equation. Okay, so we have discussed it in the last class. Now we will try to implement the multiple linear regression. For that, I am just opening the um, Jupyter notebook. I have already shared the multiple linear regression. See this one, linear regression Boston house data. So this one I have already shared with you in the WhatsApp group. Please download. And along with this, I have shared you one dataset also, Boston1.csv. Okay, I will execute the first one, first line, first cell. See, executed. So here I have imported NumPy, Matplotlib, Seaborn also I have executed. See, this Seaborn means it's again a visualization toolbox or visualization library. Similar to Matplotlib, we have a visualization library named Seaborn. Now, this Seaborn will give you elegant visualization. That means some of the visualization we can have more clearly or more elegantly using Seaborn. So that is the reason why I have called or imported Seaborn. That's all. So I have imported Seaborn also. Then Pandas, you know what is Pandas. So I have imported these libraries. Then I will input the data sets to Boston. Boston is the object name to which I am assigning the pandas, the imported data set in a pandas data frame format. The data set is there in the Boston.csv, Boston1.csv that we have imported as a pandas data frame to Boston. Now I am printing the Boston. See, this is the data set. See, you can see here we have 506 rows. Now, previously we have inputted only 30 data sets, 30 number of data for our salary prediction. Now, at that time I told you that that was just for explanation purpose, but here I have inputted 506 number of data. Okay, so 506 into 14 columns. Now you can see here the first column is some cream, then SNC. These things are some what to say, some features, some inputs which is related to this MEDV, median value of the property. So here I'm not going to explain the entire data set in detail, but I will tell you this median value. MEDV is the output. This is the value of the property. Okay, this is the price of the property. It is in what to say, million, or so maybe in million or somewhere, some figures. Okay, I don't know the exact value, but for the time being, assume that this is the value. This is the price of this particular property. So this is the first record. This is one record of a property having these many parameters, these many input values. Okay, so you can see this is a tax. This is these are some values. We no need to go into details. So if you want, I can give you. But as far as our task is concerned, this MEDV is the MEDV. This is the output. All other columns are input columns. That's all. This is the output. MEDV is the output, and all these columns are input columns. So if you want a clear explanation, I can show it. Boston data set. See, this is the Boston data set. See, yeah, here in detail it is available. See this, yes, yes. This MEDV is the median value of the home in $1,000. Okay, this is not in million. This is in $1,000. MEDV is in $1,000. So this is $24,000. So this is 21.6 thousand dollars. So like that. MEDV is in $1,000. Unit is in $1,000. Now, like that, you can see what is the first column name. So here, CRIM. So this CRIM indicates a per capita crime rate, per capita crime rate by town. So like that, for each and every column name, there is a definite definition available. See, Isden indicates the proportion of residential land zoned for lots over 25,000 square feet. So, no need to go into details of this, but for your information, I have shown this. That's all. Now, for me, what is important is the output and input. So, here, MEDV is the output and the others are input values. Now, based on these parameters, based on these many input, based on these many inputs, this is the corresponding output. So like that. So that is the thing we are going to see here. Okay, now those who want the clear explanation of these columns can go and search in the Google, and you can get those details directly from the Google. Okay. Okay, so as of now, you assume that this is the output, MEDV is the output, and all other columns are input columns, input values. Then, what is the next task? I am just taking that Boston into a new data frame, Boston DF. So this is to preserve this data set for the future use if it is required. Okay, so this particular step is to preserve the actual data set for a future use if it is required. Now this new data frame Boston underscore DF contains the Boston data set. Now the Boston data set that we have here is available in Boston DF. Now whatever change we will make on Boston DF will not be affected in Boston. Okay, so in order to preserve the data set in Boston, I am just taking that Boston data set into Boston underscore DF, and I am going to proceed with Boston underscore DF only. Okay, so that this Boston data set is not going to be affected. Okay, now from this time onwards, I will be using this Boston DF only, not Boston. Okay, now what is the first one we need to know? We need to know any null values are there. Okay, so that thing we have seen in our pandas pandas operations. Now how we will check any null values are present? This is the way we have seen it already. Pandas df, sorry, Boston df dot is null dot sum will give you under each column crim is a then how many null values are there. Okay, so here directly you can see the crim column contains no null values. So similarly, all the columns contains zero null values. So we can easily proceed. Now, if there are any null value, we have to fill up that null value. Okay. Now, since there are no null values available here, we can go directly. If there are any null values available, we have to use appropriate methods to fill up those null values. So we will see one such data set in our following sections. Okay, now just this head, you know the use of head. This step is just to show the use of head. We have seen already. First five values will be displayed. Then, if you want to know the information, more information, you can use bostondf.info. This also we have seen in our pandas class. So you can see the first column that is crim contains 506 non-null values and the data type floating point. Similarly, Isden contains floating point. See this CHAS contains integer values. So like that, if you want to see the if you want to see more information about the content of each column, you can use this info. Okay, uh, up to this you have tried. Just try at your end. Now here, what is the difference compared to the previous salary prediction? Here, multiple inputs are there. So these are different inputs, and this is the corresponding. This Medivi is the corresponding out. Okay, that is the only difference. Now these steps are just to know the information about the data sets, whether any null values are there or the data type of each column. Is it okay up to this? Shall I proceed? Only one reply I received. Others are doing or okay. Anyway, now next step is feature selection. So that means we have 14 columns. What are the 14 columns? CRIM, SDN, INDEX, CHARS, NOx, RM, age, DIS, RAD, TAX, PT ratio, then black, then LSTAT. So these are the input values. So we have 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 columns as inputs and one column as output. Okay, so out of these 13, how many are relevant inputs? That means features, relevant features, we can say that we have to determine. So some of the inputs may not be contributing to the mid value, median value, mid V. There may be some of the inputs that may not be contributing directly to the mid value, MEDV. So we need to find out that. So by seeing this, we cannot identify. Okay. So how to select the feature? The feature selection is very much important in machine learning. I told you earlier at the introduction class. Okay. So how to select the right feature from these 13 inputs? Okay, that is an important task because the entire accuracy, the overall accuracy of the algorithm depends on this feature selection. Now, by seeing this, we cannot identify directly. Seeing this will not be helpful for us to identify which is the right feature. Okay, so the method, the most common used method is find out the correlation between the input values and the output. Okay, for that, so that is the feature selection. By finding the correlation between different inputs and output, we can say whether these inputs are related to output. Okay, thereby we can find out the relevant features. For that, we are using this correlation. Correlation value lies between -1 to 1. Okay, now I told you we have the data set in Boston DF. Now, just by using this code, Boston DF dot correlation, this just by using this correlation function, CORR. So Boston DF dot correlation will give you the correlation. See, so this will give you see the correlation between all the variables. So that means crim to crim. What is the correlation? One. Crim to Isden, what is the correlation? This much. Crim to Indus, what is the correlation? This much. So, like this correlation function will give you the correlation between all the variables. Now, here also, see, okay, only this much. Okay. So you can see that this will give you the correlation between all the variables. See, all the diagonal values are, see here it is 1, here it is 1, here it is 1, because the correlation of that variable with itself will be 1. Other things are, see, Z and the correlation between Zn and CRIM is minus point 0.2 something. Okay, so by seeing this also, it is difficult to find the mostly correlated features with the output. Okay, so there is one more method, the same method only, but we are plotting that correlation using a heat map. Okay, I will show you the heat map. See, this is the heat map. Now, by seeing this, we can easily identify the correlation, which is the highest correlated value with the MEDV. We can see. Now, I will tell you that later. And before that, what is this heat map? This heat map is actually a pictorial representation of this correlation itself. Pictorial representation. So that particular diagram is known as heat map. So this heat map is available in SNS. So SNS means that is the Seaborn library we have already imported. And I told you that this Seaborn library is a visualization library similar to Matplotlib. Okay, so that heat map is available in Seaborn only, not in Matplotlib. So that's why I have called this Seaborn. Okay, so why I have called this Seaborn means this heat map is available in Seaborn. So we have called the Seaborn as SNS, a short name SNS or alias name. Now using that SNS, we will call the heat map. So SNS dot heat map of the same Boston DF dot correlation. Sorry, the same Boston DF dot correlation. That means the correlation. That means the one we have seen just now here. I told you heat map is just a pictorial representation of this correlation. Okay, now we are going to represent that correlation in a heat map. Now this annotation is equal to true. So this annotation means, see, over each column, the corresponding correlation value is being printed. See, it is 1 here, it is point 0.2 here, so like that. First, you see the first row, first value is 1, first value, second value is point 0.2, so like that. Every correlation value has been printed over the heat map. Now, in order to have that printing, that annotation, this annote is equal to true. If you cancel this, if you are not using this, you can see directly those values will not be printed. See, those values will not be printed. Instead, you have to find out the correlation by seeing the color. Now, you see the right side. See, there is one means this light color. You can see here. One means the light color. Then, if it goes to -1, it will become dark. So like that, by seeing the color, we can say there is a high correlation or low correlation. But it is always good to have the annotation for, see, now it is clearly, we can clearly see what is the correlation. Now see, by seeing the heat map, we can see, I told you this med value, MEDV, just a second. Okay, just to see here. See, this is the, this med value, med v is the output. Now all others are inputs. Okay, all other this CRIM, SDN, index, all these are inputs. Okay, so in this, you can see with this mid value, this crim is having a correlation of minus 3 point minus 0.39. Again, I will show it. Okay, you see here this mid value is the output. You can see here also or here also, no issue. Okay, so for simplicity, I am showing here only. See, with this mid value, this crim is having a correlation of minus 0.39. Now, similar to that, with the mid value, MADV, this Zn is having a correlation of 0.36. So, like that, we can find with the mid value, mid V, what are the correlations this mid V is having with other inputs. Okay, so for this purpose only, we are using this heat map in order to see the correlation of inputs with the mid value. Now here, what are the inputs? As I told you, this crim is a done. These are inputs, and this mid value is the output. Now here in the heat map, you can see the corresponding uh, correlations. Corresponding correlations. Now, by seeing this correlation, we can select the appropriate feature. Now, here, uh, by seeing the correlation, which input is having the least correlation? Which input is having the least correlation with the mid value? Which input is having the least correlation with the mid value? See, minus is okay. Minus means negative correlation. That is okay. Minus 1 to correlation varies between minus 1 to plus 1. So minus 1 means correlation in the negative direction, maximum correlation in the negative direction. Plus 1 means maximum correlation in the positive direction. Okay, now by seeing these values, which value is having the least correlation? See, this 0.18 is having the least correlation because 0.18, that is the lowest positive value. Okay, 0.18 is having the lowest correlation. Similarly, if you check, you can find less correlated value. See this 0.36 is somewhat correlated. Similarly, minus 0.39 also there is somewhat correlation. This minus 0.48 somewhat correlation is there in this. So like that, this point 2 is also a less correlation, but it is okay. Let us keep it. Okay, so by seeing this, the CHAS is having the lowest correlation. Now, you need to discard this feature because this is not going to affect the output seriously. Now, similarly, you can discard this feature also, this input also, because there also it is 0.25. But we are just keeping this. Now, if you want, you can delete that too. No issue. Okay. Now, for the time being, I am just discarding this particular input because this is not going to contribute that much to the meta value. I think this is understandable. Now, you like this, you can delete if you want. You can delete this 0.25. This particular feature. This also you can delete. No issue. So that is the thing we have done here in the program. See, we are going to drop that CHS because it is having the lowest correlation with the mid value. Okay, similarly, if you want to delete that other column, the other column is DIS. See, DIS is also having low correlation, 0.25. If you want to delete that too, you can do that too, no issue. But here I am deleting, I am dropping only CHS, least correlated feature input. Okay, so Boston DF dot drop in that which is the column to be dropped, CHS. Now, in order to show that it is column, you have to give axis is equal to 1. So, by default, it will be axis is equal to 0. That is for row operation. But here you want to delete a column, so you have to show axis is equal to 1. Otherwise, it will throw error because by default, if you do like this without this axis, if you do like this will try to delete or drop a row named chas, but you know that there is no row named chas. So dataset contains no row named chas, only chas, only 0, 1, 2, 3. So it will throw an error. Now, in order to show that it is a column, we need to include axis is equal to 1 here. Okay. Now, in the dataset itself, we can see chas all are zeros. In the data set you can see this chars column contains mostly zeros, so that is why it is showing least correlation. Now here also Zn also some zeros are there, but when you see the correlation value, Zn is offering 0.36 correlation. That is okay, no issue. But this chars contains uh, least correlation, least correlated input with the MEDV. Okay, now drop chars, then axis is equal to 1, then in place is equal to true. Now, in place is equal to true means now we are just altering the actual data set in DF. Okay, if we are not giving this in place is equal to true, it will create a new data set. That means this operation will not affect the Boston DF. In order to avoid that, we are giving in place is equal to true. Okay, so why this in place is equal to true? This is by default to false. By default, this in place is equal to false. Now, if you see the Boston DF again, see whether that chance is there. Just I am seeing first 5 rows. Boston DF got head. See, chas was where that chas was. See, chas was 0, or this is the first column, this is second column, index is the third column, chas was the fourth column. But see, after the operation, after the dropping operation, see whether chas is there. No, chas has been dropped. Okay, if we are not using this in place is equal to true, what will happen is the Boston DF will not get altered. Okay, that is the problem. So that is the reason why I given this in place is equal to true here. Now I will show it here if you want. I am not giving that in place is equal to true. I am executing this. I'm sorry because already charge has been dropped. Now we cannot drop charge again. So that is the error it is showing. Now I will show it later when we execute it. When we complete this, I will show you with in place, without in place, what will happen. Okay, so I'm just leaving this for now. After executing the complete program, I will show you with in place, without in place, what will happen. For the time being, assume in Boston DF, we have this altered data set. See here, chassis is not there. Okay, so we have the relevant features now with the lowest correlated feature or lowest correlated input chas dropped here. Okay, so we have the new data set in Boston DF dot head. So this is our new data set, Boston DF dot head. Okay, now you again you see this contains both the output and the inputs. Okay, now for the regression, we need to split the output and input. Okay, for that we are going to take the output value. Okay, so for that we are going to take the input values to x and the output values to y. Now, how will you take the input values to x here? Now, here I have shown a different way. So previously, when we implemented the salary data prediction, we have used the ILOC method. But here I am not using ILOC. Now, here also, if you want, you can use ILOC. You try at your end. Okay, so here I am just dropping the med value. That is enough because med value is the output. So I am just dropping that column. That is also okay. So instead of using iloc or loc, by simply using this drop operation, we can drop that medv column and you can keep the input columns only. So that is the thing I have done here. X is equal to Boston DF dot drop medv. Access is equal to 1. Why this access is equal to 1? To show we have to drop a column, not a row. Okay, now similarly to y, I am taking the output column only, medv. So for that, Boston DF of medv. Now here also you can use iloc or log, but I am using this one only, this method only. That's now when I execute this, I have input into x, output into y. Now let me show the input, 5 values. See, the input contains up to LSTAT only. medv is not available here. Now medv I have taken in Y. See, medv means this is 24, 11 like that. See, 24, 11, 34 like that. So I have taken in Y. So the X contains the input features, output contains in Y. Output is there in Y. Input is there in X. That's now we have separated input and output. Okay, so here you can see a difference in the uh, appearance. See, here is the data frame we are seeing. See, here is a data frame. Okay, two-dimensional. But see, here is a series only. It's one-dimensional because the output is only one column, so it is only one-dimensional. We are seeing a see. I will show you the type. See, Y is a series, and X is a data frame. That's all. That is why we are having a different appearance. That's but all are same. Both are pandas uh, data structures only. One is data frame, one is series. That doesn't make any difference. Don't get confused. You might have confused like this is having a column name, but here no column names are available. This is because here we are seeing a pandas data frame. Here we are seeing a series. That won't affect the result. No issue. Okay. So here, if you use lock or iLock, you will get a data frame like this with one column only. That's all. You just refer the previous. You just refer the previous program. So in that I have used iLock only. So when you use iLock, you will get a pandas data frame here. So at that time you can see that there you can see that there is a column name also named Medivi. Okay, yeah, that you do at your end. Anyway, this is going to affect your output. Okay, so we have the input and output. We have the input and output. Now, what we are going to do is, as I told you in the previous implementation of the salary prediction, we have to use some scaling, some normalization method, you can say, because see input you can see here input value. See when you see the input value, see different columns are there. Different columns have different ranges. See, one column is having one value. See, this value 4. So this value is 296. Very much different. This is 0.00. This is 18. This is 2 point. This is point 0.5. This is 296. So that much variation is there. So here it is 396. So between columns, there are different ranges, ranges of values available. Okay, so in order to, so that means the range of values in each column is different. So in order to normalize all these values, so we need to bring all these values within 0 and 1. Okay, so that is the usual process we will be doing in linear regression. So we will bring all these values within 0 to 1. Okay, so for that purpose, we will be using some scaling operation. This is just to bring all those column values between 0 and 1, just to scale down. That's all. No, no, actually not scaling down. We are scaling to between 0 and 1. Now for that, we have to call a min-max scaler, which is available in sklearn.preprocessing. Now this min-max scaler is not the only one. We have standard scaler available. The different scaling methods are available. You just search in the website, you can get different scaling methods. Okay, so this is one scaling method. So this will scale all the input values within the range 0 to 1. Okay, so I am importing that min-max scaler and I am taking into an object named scaler. So scaler is equal to min-max scaler of feature range we are giving between 0 and 1. Now what we are going to do is we are going to transform our input values which is available in small letter x. See, our input columns or input values are available in small letter x. So this one I have purposefully given small letter because we are going to scale it into a new capital. Okay, so that means we are going to scale this input values into scaled values, capital X. So for that, that min-max scaler is available in the scalar object. So scalar dot fit transform. We will transform and fit that X to the corresponding scaled values. Okay, now these scaled values we are converting into a data frame and we are displaying it. That's all. Okay. I have not executed this. Let me execute. See, these are the scaled values in X. Actually, I will show the head. See, first five values only. So you see the actual x value, small x. See it was 0.00632, then 18. Those values scaled to zero point 0, then 0.18. Scaling happens. See, all these values are between 0 and 1. All these values are between 0 and 1. So that is the meaning of uh, normalization. Okay, so if you have this normalized values, scaled values, then the linear operation definitely will give you good results. For that purpose only, we have scaled all the values to this 0 1 range. Okay. Now without that also you can do, because we have already done the same thing, but this will give you maximum result. Okay. Now see, our inputs are scaled. Now, so here there are no column names available. As I told you, this doesn't matter. Column names are not available. If you want, you can give the column names too, but that is not necessary for our purpose, because we are going to use these values only, not the column names. Okay. So anyway, we have the input in X, capital X. Now what is the next step? We have input. We have output also here in Y. Output is where? In Y. Input is there in X. Input that was there in small x, we have transformed into capital X by scaling. But output is available in Y. This we are not scaling. We are scaling only inputs only. Okay, so we have input and output. Now what is the next step? Train, test, split. Now for that, we have already seen this train, test, split. Now use that train, test, split. Before that, you call it from sklearn dot model selection. Now you use this train, test, split, input x, output y, test size point 2. Now random state I will explain you later. Random state you give some number 5. This I will explain later. Now when you execute this, see, now again, if you want to print these values, what is there in x train? X train. You can print it if you want. See, these are the values in x train. Anyway, this doesn't look nice, so I'm not saying these things, because as I told you, we have 506 values here, 506 rows available. So it is very difficult to see these things. So I'm not visualizing these things. Okay, so assume that we have values in X train, X test, Y train, and Y test. Now we are going to train the model. How to train the model? First, you have to call the linear regression function. Linear regression, take it into an object, lin model. Now fit that model to X train, Y train. Now we have our model in lin model. We have our linear regression model in lin model. Okay. Now what is next step? Testing phase. For that, you use that lin model. So lin model dot predict of input x test, testing values. Now you get the corresponding y test predict. Okay. Now you have to see the performance metrics. So for that performance metrics, I have taken these measures, performance metrics, MSC, RMSC, and R2. Okay, so before that you have to import these. Now from sklearn dot metrics, import mean square error. From sklearn dot metrics, import R2 score. Now first of all, I am getting the MSC value to MSC. MSC is equal to mean square error of y test predict. So y test predict means this one. Y test means the actual Y test. We have seen already. Corresponding to this X test, what is the actual Y test? This is the Y test. This Y test predict means which is the predicted output for this X test. Now we have seen this thing in the previous implementation. Now between these values, you try to estimate. This will estimate the MSC, and it will be saved into MSC. Now similar to that, root mean square means it is square root of this MSC. Again, I am writing square root of mean square error of y test predictor, or you can directly use this MSC itself, no issue. And this square root function is available in numpy only. So np dot square root of this mean square error. Why this np dot sqrt? This sqrt means square root which is available in numpy library only. So np dot sqrt of this mean square error will give you root mean square. Now R2 score, so use R2 or R square. So R2 is equal to R2 score of y test predictor. Now you calculate all these things. What is the error? Y test predict. Oh, I have not executed this line too. I will execute that and I will execute this. Then I am printing the MSC. I am printing the RMSC. Uh, I'm printing the R2. Now see the MSC value, it is 21 only. Previously it was somewhere around 44,000. I forgot the actual value. Linear salary prediction. Too much error was there. See here. See, this much was the MSC. That much high. But see here, when you do the scaling and all, and with the increased number of data, see, the MSC is this much only. Now root mean square is this much only. It is just the square root of this MSC. Okay, R2 score is 0.72. Okay, that's all regarding the performance. So this much is enough. Now you have the prediction. You give a new input. So here input means what input? Here what is the actual input? So this is the input we have given. This 0.000, 0.18, So this is the actual input we have given. We have given. So you have to give the same input in the same fashion, not the same input. We have to give this many inputs. How many inputs are there? 12 inputs. Actually, we had 13 inputs. So from that 13 inputs, we have dropped one input. So 13 minus 1, we have 12 inputs. So we have to give these 12 inputs for the prediction. Now I have given a random input here, 12 values. See here, I just used the lin model dot predict of some 12 values, some arbitrary values I have given with a comma in between. 12 values I have given. So lin model dot to predict. Now I have taken the prediction value into predicted price and I have printed that predicted price. See 27.88 I am getting for this particular input. So what is this input? This input is the input we have given here, scaled input. Now if you have given scaled input, you have to give scaled input here also. That's it. So this is how we will have the prediction for a new input. Okay, that's all. Nothing more. What is remaining is, or what else you can do is, Now you have a good model because this much R2 score is there, this much RMS is there. Now you try to save this model somewhere. Where is the model available? Lin model. In Lin model, the model is available. You save that Lin model somewhere in your memory. That means ROM or somewhere. Then you take that Lin model into production. Production means you what to say, you deploy it somewhere in some cloud or somewhere. Amazon Web Service is available. Microsoft Azure is available. So somewhere you deploy it. Before deploying, you have to create the user interface. Then only you can deploy. So this is how we will have the prediction using linear regression. So I think you understood what I have taken. Okay, so similarly you can drop this 0.25, this one, or I will show it here. This 0.25 correlation. So this is least correlated. The next least correlated. So you can delete this one also, and try to have the uh, prediction. Now there, then you will get a different result. Okay, so that's all about the linear regression. Now this one, this random state, I told I will explain. Now I am explaining that. Now what is the need for this random state means? I have shown you this X train, X test, they will take random values. They will take random values. So initially I have shown you in the previous linear regression salary prediction. See, when we have seen the X train, see, X train, random values they have taken. Random values means random columns. From different random columns they have taken. X train 18, 4, 11, 9, 1 like that. Okay. Next time when you execute this, again next set of random values will be taken. It will not take the same 18, 11, 9, 1 again. That will affect the result because each time when you execute this line of code again and again, now the set of values this X train is going to take is different. That will affect the entire result, isn't it? Now, in order to avoid that, we are going to have a definite pattern. That means if you are keeping this pattern, that means 18 first, then 11 second, then ninth row, third, then first row, fourth, then 15th row, fifth. So like that, if you are trying to follow or use the same pattern, now you have to give a random state here, random state. Random, see this one, random state is equal to, you give some value, some arbitrary value, random state, you give some arbitrary value, then you execute. Now whenever you execute it again and again with this random state is equal to 5, it is going to select the same number of rows in the X train. Similarly, in the other X test, Y train, Y test also. It will select the rows in the same order, not in the same order, not in the same random order, again and again. Whenever you execute it, whenever you execute this line of code again and again with the same random state value, you are going to get the same result. So it is acting like a seed value. Seed value. So this is acting like a seed value. Now, if you want a different seed value, that means if you are giving 6, this particular pattern will be saved for this particular 6 value. So like that. Okay, so you can change this random state to any value you require. If you execute the same line of code with the random value 5, then you will get a pattern. Each time you execute, you will get the same pattern. Now, if you change that random state to some other value and execute that value again and again, you will get the same result again and again. That's all. Now, I will show it here itself. Uh, this one I have executed once. Now, if I execute this again and I am displaying the extreme, see, this time it has selected a different set. Initially, it was 1811. Now, see, this time it has selected a different set of data in a random order. Again, I am executing this. Again, I am printing the extreme. See, this time it has selected different values. So, this will happen if you are not giving a random state. Now, if I give a random state here with some random value 6 or 55, now I am executing this. See, for this 55, this particular pattern is selected 10, 16, 12. Now, if I execute this again, see, the same 10, 16, 12 will be selected. Now, if I execute this again and again, I am printing, sorry, yeah, same I am getting. See, there is some problem here. You execute it once again, you will get the same. Yeah, again, I am getting the same result. So it is working properly. With 55, how many times you execute, you will get the same pattern. See, 690. I am executing it again. See, again 690. Again, I am executing. Again, it is selecting 690. Okay, so for keeping this order as such, we have to give a random value here, random state value. That's all. Now, one more thing I have not explained is this in place is equal to true. So that I will explain here. Just I will clear the outputs. I will show it here. I'm executing this. Okay, now you see, if I am not using this in place is equal to true, okay, I'm not using that in place is equal to true, executed. So I'm getting an output here. But you see, when I show the Boston DF again, see, that chance is there. But here you see, that chance is not there because actually our intention was to drop the chance. So it has dropped the chance here. But when I am printing that Boston DF again, when I am printing that Boston DF again, you see that is already there or it has not been removed. Okay, that means this operation will not affect the Boston DF. This operation will not affect the Boston DF, but it will show an output. That's all. With that, CHAS is not there, but this operation will not affect the actual Boston DF. That means actual Boston DF will not get altered. Now, in order to change the actual DF, We have to use this in place is equal to true. In place is actually false by default. Now we have to make it true. Now when you see this, again I have to execute this because already charge is dropped. Okay, I will see it. Okay, it is working. No problem. Yeah, because I have not used in place is equal to true previously, so it is working now. Okay. Now when you see this, see now you see Boston DF. When I am seeing it again, that charge is not there. But previously this charge was there when I show the Boston DF again. Once again you try to uh, print that Boston DF, charge will not be there. The charge is not there because we have used the in place is equal to true. If we have not used this in place is equal to true, this charge will not be dropped in the actual Boston DF. That's that is the difference between using this in place is equal to true and not using in place is equal to true.